All right, now we're back on all the platforms. Sorry if we dropped you. So, oh, it's only 6:01. Well, that's why you start early, in case you got something screwed up. Right. Let's copy that, and let's get you set up here in oh, Jesus. We'll do that here then. We'll just get the invite over to the wife / moderator. Let's see. Looks like it's behaving on Facebook. Well, at least it's there on Facebook. It's not playing yet, I don't think.
No.
Come on. Quit moving things around. I really am stressing this machine. Looks like that's, we'll have the whole. It can't seem to bring up the chat. All right. There it is finally. All right. You should get a Facebook link to the StreamYard. Maybe. I can't tell if it has or hasn't.
Mm-hmm.
All right. There we go. We can be done with the resource drain of Facebook. All right. I got everything wrapped up. Oh, 7 viewers, a record for my streams. Thanks for joining. We finally got all of that fixed up. We'll get started presenting here shortly. Pay no attention to the puppy playing with the toy. She really, really loves them. So full screen, that screen. Go ahead and share. There we are. And I really like this format. I didn't want to go full screen. Exit full screen. There we go. I'll find it, figure it out eventually. All right. We're pretty much going. My face in the corner there. That's the one I wanted. Now we'll close it with that. There we go. We'll get everything figured out eventually. All right. Let's get this going. What is that?
Me.
Oh, I see. There you are.
I just turned it off.
There you are. Well, that should let you see all of the comments and squeaky, squeaky. Yes, you're a good puppy. I never let you do what you want. I squeaky. All right, so we're here. We've got it going. We got some squeakies in the background just for fun. But let's get our program running here. Let's see. We're going to just not hit the hotkeys on the wrong screen. That's what we're going to do. Come over here and hit the hotkeys. So as you can see, running the emulation or the simulation on the hardware simulation is a little bit on the slow side. But it will let it get all going here. And actually we'll be ready to type something in down here once it finally gets all of its text printed. Most of this isn't actually applicable to this view. It's usually the emulator that I run. It's so much faster and a little bit more 90s. This is the actual hardware emulation that's being done in Logisim Evolution. It's actually my private what do you call it? Fork of Logisim Evolution, because they kept changing things in ways I didn't like. So I kept this version. So as we eventually get to the user prompt, it's coming, honest. There's a prompt here sooner or later. There we go. So now as I type stuff in down in this box, you'll see it'll slowly grab those in, put them into the text input, hit enter, and it prints it back out. So that's just our little hello world program. And just to show you what is actually happening under the sheets, we'll go down into the computer view and put that. So here's our processor chip connected up to the actual output display. Here's an internal keyboard that I can use to, or we can actually look at the lowest level, which is the actual wiring diagram of the processor. Here we have our ROM that's running our program, and the RAM that is used to store the data as we type it in and that kind of thing. Up here is the sequencer. And let's just get going on what the problem is to begin with. And that is that when I laid out this instruction matrix, it was designed, the main idea or the main issue with the instruction set design was I needed to be able to handle a lot of moves from one register to the other. So if we take a look back at the wiring diagram, you'll see that the ROM is, get it in here, the ROM is input 1, the RAM is input 2, register A is 3, 4, 5, 6, and 7. So each of the byte registers are numbered, and all of those line up with the instruction set. Oh, come on, you. There you. So the way the instruction set is laid out, that normally what we have to do to move data from one register to the other is tell the first register or the source register we want to do an output enable. So we have the output enable, and then we have the destination where we say load. So it's actually backwards. It's always destination first in this scheme. So destination, for example, the load, let's see, we'll use load AB. And load AB says load into register A that which is in register B. And so register A is number 3, register B is number 4. And so the instruction for load AB is 3, 4. And that more or less lays out and works for pretty much all of these move commands, all of these ones in light blue. But of course, there's no point in moving from 3 to 3. And so the diagonal became all the special instructions like no op and halt and all of the interrupt commands, then decrement and increment the stack pointer, interrupts, and a reset. So instruction AA is reset, and instruction 11 is halt. And back when we were hand compiling and hand assembling stuff, it was quite annoying to have to do that manually. So this helped, I could just look at the source instruction in the bytes and know what it was doing because that's how it was all laid out. Now, having said all that, I screwed up when it came to these 2 rows. So seeing if this will highlight for me. I'm really going to love getting my old machine back, I got to tell you. So these top 2 rows, the DRAM based on the stack pointer and the EEPROM that can either be the data register or the stack pointer. These 2 rows here are actually backwards in the logic in that the destination for EEPROM should be 1 instead of 2. And so I kind of screwed these up when I put it together. And, it all works. I managed to make it work because for example, the load AB command, it is instruction 3, 4. And over in the sequencer ROM, instruction 3, 4 for load AB has an entry of 0048. So the way this basically works is I take an instruction, I use that instruction as the address into the sequence map ROM. That gives me 16 bits. Those 16 bits are, as you can see, all the different highlighted 48s here. Generally, the sequence 48 does all of those moves for me. So sequence 48, the last 2 are the last byte of these 16 bits, is then used to move the sequencer to that location. So in this case, it's 48. So 48 handles all of the loads and write commands, and it consists of 4 maneuvers. These 32-bit values in the sequencer are used to individual bits to turn on and off the write enables and the output enables, and also control initiating the ALU instructions and so forth. So it's a pretty complicated layout of what all these bits mean, but it's all documented pretty well. So these first 2 are the instruction low and the instruction high nibbles, which is, again, the output enable and the load or write enable. So this is a pretty typical design for a complex instruction set machine that's run off of microcode. This whole section with the sequencer is the actual microcode. So you could actually edit the microcode and redefine what the instructions do. And I'm actually still doing that. I haven't got all of these instructions in. Some of them don't make a lot of sense, like why would you move into the D register the contents of the half of the instruction pointer? It's just not something you would typically do. So I've got those highlighted as perhaps usable for something else. And as I write more and more complex instructions and more complex programs, I'm going to eventually, run into other instructions. In fact, one of the ones I really like is the addressing modes. Right now, it takes me like 4 different separate assembly instructions to move data from one 2-byte register to another 2-byte register, or 2 bytes from RAM into one of the 2-byte registers, either the DR or the stack pointer. And that just is a lot of overhead to write over and over again in your application. So I probably will get rid of some of these jump commands as well. Mostly these are jump shorts and jump longs. Jump long says jump to a 2-byte destination, and jump short says jump to a 1-byte destination. The jump short it's not very useful. It really needs to be not a short, meaning just the lower byte of the address, but a relative number. So you would jump from this current location in the program to -2 bytes, for example, or +2 bytes. And that's probably more useful than just a short instruction. So we'll probably redefine those later. Squeaky, squeak, squeak. Hey there, how's it going? Thanks. Is that 7 Etso?
Yeah.
Etsu? All right. So yeah, as I was saying, we've like I said, we'll probably redefine these later, but we can redefine them by simply modifying the sequence, either both the sequence map instruction that we start with, as well as the actual sequences in the sequencer. And this is also why your complex instruction set machine like x86 will take, in this case, it takes 4 cycles, 4 steps through the sequencer in order to execute any of these load commands. And so some instructions are very short, like that one, the 3 or 4, and then to return from a long call, there's a good bit more instructions that have to be done. Of course, at our actual boot sequence where we zero out each value in the registers and then put FF in the stack pointer and then go to the first byte in ROM and load the first 2 bytes in ROM and load that up as our entry point for the rest of the program. All of that is done in these first 16 steps. So there's 16 instructions just before the processor even gets to main. And then after that, each individual instruction takes a varying amount of time depending on the complexity of the instruction. A lot of them only vary by, either like the jumps, the conditional jumps for long jump if carry or not 0 or borrow bits are set in the ALU. Those actually end up being all the same sequence, but they vary based off of those ALU bits. And that's actually described within these other flags that we have here. So this allows you to essentially take or get a lot of instructions into a small sequencer. This has only got 256 instructions that fit in our sequencer. Could be more. In a more complex design, you would see your microcode, and your microcode logic would actually just include all of this in one ROM chip. In other words, you'd do one single lookup for your instruction, and then that instruction would start somewhere in the sequencer for you. And I set it up as separate ROMs. This one is a 16-bit and this one is a 32-bit, because generally the actual microcode ROM in something like the 8051 microcontroller is going to be something ridiculous like 17 inputs and 56 outputs or something like that. Something I couldn't really readily design in Logisim. Plus, I figured maybe one day I'll build this out of hardware, and it's just easier to find 16-bit and 32-bit ROMs. Of course, finding them where they're just 256 entries long, that's harder to do. There's really no ROMs left in production that are that small. So back to the problem at hand. In this instruction, which is store using the stack pointer into DRAM the contents of register B, SCB, which is instruction 1.4. We look at instruction 1.4, SCB, and of course all of the rest of them. The reason I can get away with using the same sequence is because the information about from and to registers are already in the instruction. Like in Akira, huh? I'd have to double check that one. I'm not sure on that. So these 42-bit or sequence 42 that starts at 42 in the sequencer has this byte here, or this nibble here. It could be 0, and the existing flags would already work because the it would just draw from the fact that the instruction was 2 in the first nibble instead of having to use it here. So these two rows are swapped as far as what register from to register, but it's patched up in the microcode because the microcode's flexible enough to use a different register than the one that was specified by one of the nibbles in the instruction set. And I had to do that because otherwise I wouldn't have been able to initialize everything in the start of the sequencer and when the processor powers up. Obviously, in the implementation, you just mem set everything; it's all 0. But actual hardware, when you first turn it on, it's going to be floating. It's going to have weird bit values, so that's why you want to initialize it. So really, the fix is if I change SCA through RC3 here, this top row of 1s, if I move that down here and swap it with SCA to RE3, if I actually swap those rows so that it lines up properly, all I'm really doing is changing this 2 to 0 and the next row down, which is instruction sequence 4C, this number from 1 to 0. So I'm changing 2 bytes or 2 bits. It's not going to make the instructions go faster. And, I have to correct all of this, and then I'd have to correct the translation map in the assembler. When it sees SEB, it's no longer 2.4, it's 1.4. So then everything has to be all relined up. So the title of the stream was, if it's not broke, don't fix it. Should I fix it just so that it lines up on this and it sort of fits the original model? I'm kind of the mindset of no. I mean, yes, it'd be a little bit cleaner perhaps, but cleaner at the cost of a lot more testing and making sure that I didn't screw up something else while I was fixing it. And while I was looking at this and getting ready to do this stream, there was a tweet that was posted by a guy who's clearly new to programming, and by new I mean who was like, why do C programmers obfuscate their code with weird, very small variable names like S2 and S1 and these kinds of, rather than having a longer, more descriptive variable name. Now, I mentioned that yes, it cost money. Every byte was important back in the day. And so I would definitely not recommend, if I were to write this function, which is to look at a line in a comma separated file and parse it out. That's the purpose of the function. If I were to write that function today, I certainly wouldn't use abbreviated variable names. But when we started out, we had a lot less resources. Things were more important. And if you tried to write this by hand on a whiteboard, because as the guy mentions later, the person who wrote this code is a professor of computer science, and he would actually write this code on the whiteboard. You're never going to want to write out the same name over and over. And plus, what were you going to call it? String2 equals string1, or string source equals string destination, or something like that. So, does it really make that much difference? Certainly, it's only for readability by the humans. And it would help people coming into it later, but this was probably written 40 years ago when those restrictions existed, and it works. So why bother to fix it, right? Same basic. And like I said, if I were to start fresh and if I were given the task, tweet made you laugh. I bet it did. Because he was like, oh, you got to pay for each letter and then trial versions of GCC. And I was like, well, yes, you do. Unfortunately, yes, to all those reasons. Compilers had limitations. There was a cost to actually transfer bytes up to the mainframe for the mainframe to compile. All of that's historical. Obviously, none of it applies anymore. But it's kind of like programming PTSD, I guess. People got used to doing it with very abbreviated variable names. When I started with the VIC-20, I had remembered incorrectly. that the VIC-20 had the first 8 characters were significant, and actually only the first 2. So banana and bandana would actually be the same variable, and that would cause confusion. Now, even the VIC-20 manual recommended that you use more complicated variable names that would make more sense, but obviously you still had to make sure the first 2 letters didn't overlap. And of course, you had 2 kilobytes of data of program space in the VIC. So how many variables were you going to make anyway, right? You know? So in any case, long story short, I think I've come to the conclusion that I'm probably going to leave the sequencer and the instruction the way it is.
Quitter.
I'm not a quitter. Come on. Yeah. Yeah. A lot of people do.
What they say.
And that's because, you know, what more do you need, especially if you're already in this mode? I mean, this is the entire, I think it's the entirety of the, there it is. It's bringing up the image. So this is, well, it's not quite the entirety of the function, but it's pretty close. So if you're familiar with it, you know, like I said later on in a second tweet, I am much more interested in having longer comments than longer variable names. Yes, you do get an idea, a better idea of what things mean with the longer variable names. But in this case, there's a single comment in here. Oh, there was an empty file. So we break out, but that's it. That's all there is for comments. And yes, comments did cost money at the time. So to give you an idea, the program I was actually running was my Hello World program. And I've had, you know, had a variation in writing these things over the years. It's actually been a couple of 3 years now that I started this. So if you look at the whole, what do they call that? Playlist. You'll see that I actually did my original Hello World by just hand assembling it and wrote the values directly into the ROM in the emulation. So let's go ahead and bring up that. Oh, sure. Don't be where I need you to be. Be that way. Oh, goes the machine. So let's get into our programs. And if you want to follow along, if you want to take a closer look at this, all of these files, the emulator, the assembler, are up on GitHub under the project. I also have a separate GitHub for the source to the emulator and the assembler, but those really aren't totally stable yet. So I've been holding off on making that public. But if we go ahead and take a look at our Hello World assembly file, and let's just make it big, why not? So it's easy to follow along. Actually, it's not quite as easy to follow along when it's all the way on the left side of the screen. So here's the Hello World program we were actually running. And I actually tweeted out an image of the assembler commands. It's pretty straightforward. It was designed to be fast parsing and not necessarily very complex. So by and large, there's essentially two columns in here. The command column, which has to be on character 1. We're not doing a lot of complicated parsing here. And then column 3 is the next piece of information. So you've got your hashtag. You've got your hash brown, hashtag, number sign, whatever you want to call it, which is your comment character. It's pretty typical of assembly languages, which comments out the current line. And then you have things like capital W, which writes whatever this symbol's address is to ROM at the start. In this case, it's what we refer to as the reset vector. And then after the reset vector are the vectors for each of the interrupts. So after that, we need to change our current location in ROM to be past the reset vector so that we don't end up, or past the interrupt vectors, so that we don't end up jumping randomly into ROM somewhere. So, and now that we moved it off, we can define something. So these 3 lines here is the equivalent in C for those 3 lines would be char pstr hw bracket equals curly brace quote hello world, and the C compiler would conveniently include this last 0 for me. But I actually, this part of the point of this program is to use all of the assembler instructions so that I can continue to test the assembler. So we define a string, and it would actually end up being this string because we have a second new line here, but done by using what I refer to as the hex literals. And so these 3 lines are actually this single line of C. And so you can see why people moved up 1 level in languages, because it's much more compact and much more readable and maintainable. But in any case, long story short, we define a symbol, and in our case, all of the symbols are essentially global. I don't have any kind of scoping. The symbols are global across your entire program, including all the letters you load. So I do allow you to have 256 letters for your symbol names, but that's more so that I'm less likely to have a symbol collision. And right now we're having a puppy break. Come here, you. I know. This is the puppy that loves the squeaker. Look at her. I love squeakers. Give me squeakers. All right. Do not hang on to my shirt. Run off now. Go on. That's a good girl. So we basically did that over and over again. Here's a separate signal for the help string that took forever to print earlier on. And you can see it's the same kind of thing. Got some new lines. We just define a series of strings, and since there's no 0 defined until here, this is all one long string in ROM. And then we define a prompt string, which is just, like you would have on a command line tool. And same kind of thing, I could have just done /0, and instead I went ahead and did a literal 0 afterwards. So that's all of our text that we did out at top. We're getting a little flashiness, and my video's not completely tracking.
Awesome.
Yeah, we love the doggies. So then we have to set up our global variables that are actually in RAM. And so for that, we have the address instruction, which is capital A, says that that's going to be the starting address in RAM for our variables. I created it as that just so that it would be way off into the distance. I did that so that if I typed a very long string, I would actually I'd cause a buffer overflow, because there's only 32 bytes in this string, and at the end of those 32 bytes is the stack, which is busy doing stuff. So if you do type too many characters in, you'll overflow the stack and it'll go off into the weeds. Usually very quickly reboot, like all sorts of other hardware would do. So that's why it's off in that odd location. And in the C language, the compiler decides where your locations are. And in this case, the assembler does too. It just starts at whatever you tell it to. These are kind of like the .origin commands in other assemblers. So in this case, I create a symbol that's meant to be a variable, hence the capital V. And so it creates this symbol based off of whatever is the next location in RAM. And then the add 20 to the current location in RAM that the assembler is tracking gives me that 20 bytes, well, 32 bytes of space for the string. And so the equivalent of this in C would essentially be char CA string in bracket 32 with no initialization. And again, you can see why we've moved up to the higher level languages. So after that, we actually say, I want to move the origin in ROM to this location, skip past all of this stuff that we created as our text, basically, and then start loading up code. So the first thing we're going to load up is include the assembly file in the IO libs that has the functions for print ROM and print RAM. Then we finally get around to defining main. So there's our void main location. We tell it we want to print hello world. So to print hello world, we have to do it in two steps instead of the print hello world, or I guess the true C version of this would be printf hello world. And hello world, as we looked at above, has two carriage returns. So it would actually be hello world double carriage return. There we go. But we've already defined the constant hello world up top. So in this case, we just tell it load into the DR register the location of p string HW. Yes, we're going to go throw the toy into the other room, so the beeping's not quite so bad. And then we call the print ROM function, which prints from ROM, as you'd imagine. So it prints hello world, then it prints out the help string, and then we start a loop. To start a loop, we have to have a label to go back to. And since my concept of symbols doesn't really have a restriction other than in fact, it can have spaces in symbols names too. It's probably a bad idea, but it makes the assembler easier. So we define a label here, get line and print it. And essentially what this is doing is recording that get line and print it is this location in ROM. We load up the prompt, print the prompt. Then we load up into the data register the location in RAM of our string buffer, which is up in here. And then we call the get string function, which waits around for you to eventually type a carriage return. Then we write a carriage return out to the display just so that we can get a nice new line. And then we, again, load up the pointer. The reason I'm loading it again is because the get string function is destructive to the contents of the DR register. It's actually incrementing the DR register every time you type a character. So in order for it to properly print again, you have to reload it with the start of the string. And then we print stuff that's in RAM instead of ROM. And again, print a carriage return. And then we jump short, meaning we take the current location, the high byte, leave it alone, replace the low byte with whatever we recorded in here when we created that label. And so we just sit in this loop all the time. It's essentially a while one loop, if you will. So that's pretty much the background of the application. I really had no expectation of this many viewers. So I'd like to encourage you to go ahead and ask questions. The real point of this is to have an example that starts from the ground up, from electrical design and electrical simulation, I guess logical design, logical simulation. This does not in any way simulate the actual electrons. It's just the ones and zeros. So this is what I refer to as the first level of computer science, because a lot of people ask, where's the difference between electrical engineering, or the borderline between electrical engineering and computer science? And I would say it's here. If you're designing things with ones and zeros, it's computer science. Once you get below this and you're defining things as being either 0 and 3.3 volts, or 0 and 5 volts, or negative 11 volts and positive 11 volts, now you're down into the electrical engineering world. And there is a pretty fine borderline between the two. But as you can see, this was designed to be able to actually see how the information from the sequencer is decoded for both the source and the load. And those lines actually come down to choosing individual registers. And I don't know, where should we go from here? Should we do some single stepping? Let's see. I can do not just single step, but single step through the sequencer. So it's not just each instruction, it's each step within each instruction. So let's see. We have come up on instruction. Can't really see that, can you? Anyway, our next instruction that we're about to execute is 07. If we pop back over to our instruction grid, 07 is 07. Yeah, 07. Why in the world would I want to do that? Why in the world? Oh, it's basically the call instruction. So actually, it's not the call instruction. It's actually the data for the call instruction, because 80 is the actual jump instruction. Sorry. So I'm saying jump to 07 in RAM. So if we do that, you'll see we jumped back to location. That doesn't seem right. Let's see. I should probably prepare this more. Let's see. This instruction is 4C. Let's go ahead and take a look at what 4C is. 4C is load into the B register from port 0. And port 0 is my input port. Port 1 is the output port, standard in, standard out, if you will. And so it's going to load into port B, which is currently 0, whatever is waiting on the port. Well, there's not much waiting on the port. So let's go ahead and give it something on the port. And we will give it something on the port by just directly changing the register. Let's see. 64. That's some sort of character, right? Let's go back up. Go back up there. So now we have 64 in the port 0. And when we execute this instruction, what you'll actually see is we're going to execute each of the steps within the sequencer. Instruction, well, we haven't loaded the instruction. Now we've loaded the instruction in the instruction register. It says, oh, well, that's sequence 48. Our sequence is at 48 right now. And if we jump back over to the sequencer, we can see that instruction 48 starts with those flags. So we're going to actually step through all 4 of these. In this level, we actually step through the sequencer. So 48, 49, and there we go. So those steps first said output enable the port, then said load B. So because every time we output enable, it goes out onto the bus and as a whole. So now we've loaded from that port into the B register. And we're then going to do, well, let's finish that command first off. There we go. We load up instruction 82. Instruction 82 is a jump short, or jump short if there is something other than 0, something non-zero. So the ALU flag for 0 is actually reset every time we load something into the B register. And this is why you'll see so much in the C languages based off of nulls, right? Continue copying a string until you hit a null character. It's because when you load a character into a particular register, it will reset the 0 or non-zero flag depending on your processor. In my case, I have a anything other than 0 flag. Actually, it depends. Sometimes it's more helpful to have 0. Sometimes it's more helpful to check for non-zero. In some processors, there's an instruction for both. So you can jump if the register is 0, or you can jump if the register is not 0. So let's see, we're going to do 82. So 82 is jump if there is something other than 0. And that instruction is going to be taken. We're going to jump to address C once we get to it. There we are, jumped over to 10C. It's a jump short, so it's just the OC part that we copied. So this is all of this code way down at this level. It's somewhat easier to see and understand using the emulator level. So this is sort of how your electrical engineer might look at your processor as he's putting it together. Let's go ahead and I will start. I'm going to create a convenient command shell. Oof. Everything's slow. All right. So don't give me that. Repos. Open up. Programs. Hello world. There's all of our files. To bin and the EUP emulator, and we say we want hello world, the ROM image. We get our nice little emulator, although it's not nice and square like it is usually. And it actually brings up, let's do this. If I can convince it to do it. There we go. Never does work when it's that short. Okay. More or less. All right. So now in the emulator, you'll see we're at hello world assembly file line 6, and conveniently Notepad++ has brought it up on that line. We can go ahead and do our single stepping the entire instruction, right? So there we go. We jump down to the symbol main, whose first instruction is load the hello world string, right? Oh, it's one of the things I still haven't worked out is this takes the focus once it pops up. So I have to come back over here and forcibly re-click the window. So now we're about ready to call print ROM. If we call print ROM, see, we'll actually get into the EUP.io assembly source. It does a number of instructions, basically to print that. We don't want to single step through all of that, so we actually have a step return function with F7, F1 for help, as was always the design of most Windows programs. So now we've come all the way and stepped out of that print ROM function. Now we're going to load up the the next one, the print string function. Then we're going to call print ROM. If I get the focus right, again, let's just step out of that, have that all print nice and quick. And for here, why don't we just start? Of course, we'll go F5. We'll actually just run straight through. Come on now. There we are. Whew. Only getting 6 megahertz. Ugh. It's a slow day today. But this is the same program that we ran in the emulation. It runs a good bit faster, or rather ran in Logisim, runs a good bit faster here. And if I closed all these other things I have running, oh, geez, it's so slow. That's the real 80s experience. 5 megahertz machines. I tell you what. All right, let's just say enter on there. There we go. I guess I erased the whole string there because it should have said, let's see.
Why are your pipes red?
Oh, I don't know. Talking too fast, not breathing enough. Those kinds of things. I'm amazed at 96 viewers. Thank you all for tuning in. It's been so so many years of so few views, I can't even tell you. But there we go. Program runs. It says hello stream for us. What's happening?
Where do you see?
Right there it says eyeballs.
Oh.
So
Sorry, but I was in the shot.
that's okay. Cameo of the wife.
I don't have that.
You know, that's odd.
Mm-mm.
I don't know why. All right, so we're all running. You know, basically it's sitting here in the loop waiting for me to type a character, right? And of course, every time I hit the box here, I pause the program. So it's sitting waiting pause to grab a character so we can go ahead and hit F8. F8 says halt and show me where you're at. And you'll see we're down in the get string function, which says load load into register B, whatever's in port 0. Then it says jump short to get string. Well, we stopped it after it checked if I had typed nothing. So now it's going to jump back up to there because there's the definition of get string location. And let's see, we're going to go back in here. I'd already loaded into B, which is 0. So first off, we got to give it a character on this end. And then let's see. All right. So right before let's type a character. It's not showing the character. Not sure why it's not showing the character. Well, it's not showing a character because it's not echoing yet, but it should at this point. Oh, I know where we are. So here's port 0. Here in the emulation, it's showing 65. If I type some other character, there it is. It changed to 72. So now when we run this instruction on line 19 here of load into B from port 0, we should get 72 moving over to register B. And yes, we do. Now we're going to jump short if it is not 0 to getString.go, which is defined down here. Now because all of my labels are globals, I just decided as a convention that if I have a label with a dot in it, it's going to be considered sort of a local label. I mean, it's not really, but I don't report them when I do the assembly. So one of the outputs of the assembly is the down in the IO libs. So one of the outputs of the assembler is a symbol table. And that tells you all of the symbols that don't have a dot in it and what their location is in ROM. And this is typically how people would have to debug back in the day. They'd see some register value of 0124. And they'd say, oh, why is the instruction pointer 0124? And, oh, that's the print ROM. So in any case, if we do F10 again, there we go. We'll see it says that we actually jumped down to getString.go because it was something other than 0. Now we print a 0 out to the port, and that was done for the electrical thing to essentially acknowledge that we read a byte and set port 0 or port 0 back to 0 so that we would read the next byte. There it is, back to 0. Then we're going to load into the A register the constant 0A, which is character return. So you load that into A. Now A is a 0A. Then we're going to do a comparison of these two numbers, the number in register A and the number in register B. So see if I can zoom this slightly. There we go. So how do computers actually know one number is equal to the other, right? Well, in a lot of cases, it's simply a subtraction. In this case, it's minus A and B and put the result into A. That's essentially the attribution. There we go. There's the comment. So B equals B minus A. It's actually A equals A minus B. Never trust your comments. But in any case, I do the subtraction of A and B, right? We'll do that subtraction. It's 98, and it caused the borrow flag to be raised. And since if you subtract one from the other, the result would be 0. So I'm going to say jump short if it's something other than 0, because what that means is that whatever was in B, it's not the value A, not the value that was in A, because I got something other than 0 after the result of the calculation. So we're going to jump short if we're not 0 to C2, which is defined down here. And we're going to check for the next important character, which is the backspace character. So check for the backspace character. We do the same kind of thing. Load the constant 8 into A, subtract A and B with the result in A. That's still something other than 0. So now we're going to jump to OC, which is other character. And obviously, again, just like we were talking about earlier, I could make these labels a little less cryptic, but it's a fairly short function. So we're going to jump over that. Now we've got any other character. So if it's any other character than backspace or carriage return, we're going to store it in RAM. And to store it in RAM, we want to store indirectly. This is part of the problem of coming up with a 3-letter acronym instruction set, which was one of my original design goals. So you kind of run out of letters. So we're storing indirectly B. What that means is we are going to store whatever's in the B register into the DRAM indirectly, meaning using the DR register for the address of in RAM. So our DR address is what we defined earlier as the start of our string. And so we store that, and that's actually shown here. Right now it's 48 because the first time we did this, we did hello stream. And so that string is still left in memory. So now we get the lowercase r as the first line. And if you do this enough, you really begin to understand where all of the holes, especially security holes and buffer overflow problems, come from in the C language, because you're not actually erasing the entire string first and then writing new characters into it. You're writing new characters into it until somebody hits carriage return, and then you put a 0 wherever they put carriage return. So in this case, we've stored the character. Now we want to increment the DR register from FFE0 to FFE1. There we go. And we're going to echo the character out to the screen with a write to port 1, whatever's in the B register. There we go. There's our little R. And we're going to jump back up to the top of the function. There we go. Again, load whatever's in the register. So to make this short, since we're running out of daylight, I'm going to go ahead and hit a carriage return here. And there you go. You see port 0 now has the carriage return character in it. We load that carriage return up into the B register. And since it is something other than 0, anytime I load into B, I reset the 0 non-zero flag. It gives me shortens it by 1 step by not having to do a comparison with 0. So it's just a convenient bit of extra hardware to make that step easier. So now we'll read, go down to where the go symbol is. We'll acknowledge our carriage return, or rather acknowledge the character we entered. Now we're going to load the constant of A, carriage return, into the A register and the B register. And when we subtract A from A, we get 0. And since it's 0, this should fall through because we only jump if it is not 0. And then we're going to say store indirectly whatever's in A into the current location that the DR is pointing. And so that's going to change this location in RAM to a 0 because that happens to be what was in the A register. And that was our string. So now instead of hello stream, we have just R. Just very simple, small string. And since that's all we do in get string, once you type a carriage return, we place our null and we return. So we return out of that. There's our call from get string. We print our carriage return on the screen. We're going to load up. Notice we destroyed the DR register as we were typing, or we changed its original value. So the LDR value instruction will load that original value back in. And then we'll go ahead and print from RAM, which is a slightly different function from printing from ROM. Because I was a security nut. Actually, it's because I wanted to have the full 16 bits or 65,000 bytes of data available in both ROM and RAM. And this is not at all what typically was done back in the day. This was roughly modeled after the 8051 microcontroller. And it has something like 1K of ROM and just a unified memory map. So the first 1K is ROM, and then after that is RAM, and you don't have this separate bus or separate access to RAM and ROM. My original thought on the matter was that I was being sort of a security jerk, if you will. The EEPROM, or rather the instruction register, can only be read from the EEPROM. You can't modify RAM and then tell it to run what's in RAM. Obviously it would run slower, but it was kind of a concept, a security concept. And same kind of thing here. But then, of course, I come back to the fact that that's the only two places I have to write stuff. If I want to make maybe a file system or something and have that in the EROM or the EEPROM, this would probably actually, in a real implementation, my ROM would be a battery-backed RAM. And then you'd have some jumper or something on the board that told you whether or not you could actually write to ROM at runtime. That's all security and safety issues. A lot of the headaches come from in C. If you do a buffer overflow on a string and you put it very cleverly, you can actually inject instructions onto the stack pointer or onto the stack, that when you exit out of that instruction or that subfunction, you jump off into some totally different area. If you do it cleverly enough, that totally different area is going to do something like, read your keyboard and send it to China or something. I don't know. But that's where all those kinds of problems came from, is the fact that you're actually running out of RAM, and RAM is rewritable at runtime. As processors got fancier and fancier, you end up later on having memory map or memory management unit, the MMU. And the memory management unit would allow the operating system to say, here's the portion of the application that's going to be running from RAM, but that portion of memory is read only. And that all the controls are done by configuration of the memory management unit, which is under the sole control of your operating system. So, of course, we're not at that scale. We're at the much lower security level. So to avoid the need for an MMU, if you will, I just said there's going to be a separate location or a separate ROM for executable code, and it's not going to execute out of RAM. But that also means I don't have a unified memory map, so I can't readily use the same functions to read from RAM as I do read from ROM. And you'll actually see that in the instruction map. Anytime LAM is essentially load into A from RAM, and this is load into A from EEPROM or ROM, or like, again, keeping a strict 3-letter acronym instruction set means that you kind of make some compromises. But it is still load into destination from source. I just have to rename the sources sometimes to fit everything in. Just like this. This is load into A from DRAM load into A from from the ROM, and this is load into A from the ROM, but at the stack pointer. This one uses the instruction pointer, and that's so that I can have a constant like you see the instruction that we used before for the comparison where we said where'd he go? Oh, it was down in the IO function. So here, load into A from EEPROM, whatever the next byte is. This is the next byte in EEPROM or ROM. So essentially it does it based off of the instruction pointer, because the instruction pointer first loaded this instruction, then it incremented, then it loaded this contents. And all of that increment the instruction pointer, load the next byte into this particular register, all of that is what the sequencer is accomplishing. So let's see, we've been going for an hour and stuff. Really hard for me to stop when I've got this many viewers. So feel free to throw down questions, pretty much any assembly question you have. Or if you want to know any other details about this, let me know. Otherwise, I'm just going to sort of wing it and keep going as long as people want me to.
Go.
Keep going. All right.
Yeah, that's what I was going to say. You should ask questions. Ask if
Yeah.
anybody has any questions.
So let's get back to our running example here. Oop, there we go. I kind of hate the... There we go. So where were we? We were just
like a dude, by the way.
Oh, come on.
I'm not.
She's not a dude. I can attest. I've checked the equipment. Well, now.
All right.
This is not an Instagram stream. All right, so we're getting ready to print RAM. So we're going to load B from RAM based off of the contents of the DR register. So now we've loaded that lowercase r from this location in RAM into this register B. And now we're going to jump short to the print RAM.in label, which is just below it, as long as it's something other than 0. So again, you can see why strings ended in zeros in the C language, because it was convenient for assemblers and processors. So we jump short, if not 0, we're going to write that character out to port 1 from the B register. Okay, there we go. There's our R. Now we're going to increment the DR register. There we go. And jump short to print RAM, which is, it's jump because they're really close together. They're only 1, 2, let's see, 1, 2, 3, 4, 5, 6 instructions apart. So now we're going to jump short back to print DRAM, which you actually see here. Here's our ROM and our RAM, and this is jump short to address 30. Plus 0136 in the instruction pointer with 0130. And there it goes like magic. It's not magic. It's just moving bits. And now that makes our instruction pointer back up here to load the next value into B register from RAM, which is a 0. There's the byte value. Here's the string value. So we load that 0 into B. And because we loaded a 0, we're going to say jump if it's not 0. And that condition fails. And so we return back to the function from which we came. Well, I have to keep clicking the emulation window. On my faster machine, it does it automatically. That's why it's so frustrating right now. But just a little update on my main machine. I had a SSD drive, right? Nice, convenient 0.5 terabyte SSD drive. It went poop on me just before I went in to do some medical stuff. And so luckily it failed like 2 weeks before the end of the warranty. So I sent it off, they just replaced it. They didn't tell me what was wrong with it, and that no longer has Windows on. I'm pretty sure that's a blank drive with nothing on it. So all of that data is gone, but obviously we have Carbonite. So most of the useful stuff is backed up, but not the operating system. So now I'm going to rebuild this tower system, and especially considering the recent Windows, we're going to put spyware on your system just for fun announcement. I think that's going to be a Linux machine now. So we'll start doing stuff on Linux for sure. So anyway, back to our program here. We printed our RAM. Now we're going to print the carriage return out the serial port, which is kind of, you can't see. And then we're going to jump short back to the top of the loop. What are you giggling on? She's finding things funny that I don't know.
I'm like a minute and a half behind you.
Oh, well, that's why. Minute and a half. Jesus. We know there's delays in streaming, but really a minute? That's pretty ridiculous. So here we're going to print our prompt again. And call print ROM, and instead of stepping through that whole function, maybe we step through print ROM. And it's essentially the same as print RAM. It's just using read from ROM instead of read from RAM instructions. So we'll go ahead and oh, really huge delay from YouTube to X, huh? Well, go figure. It's StreamYard. What are you gonna do? It's not the free StreamYard. Yeah. I'm paying for it.
I'm just YouTube and stream, and he says huge delay from YouTube to X.
Yeah. Apparently there's a huge delay in you seeing comments as well.
God.
What the barky?
Yeah, I stopped petting.
Oh no, I can't. Oh no. So both of our dogs, one is a Chihuahua and something. She looks like a fur-covered baloney. And the other one is a relatively new dog. And she is clearly not a Chihuahua. She's a terrier. And, you know, the abbreviation for terrier is terror. But they're both from what we refer to as the attention hound group. In case John O'Hurley is listening, they should make that an official dog breed. So wife is taken off and handling the puppy. So here we are. Let's go ahead and okay, we're going to read again our string, and that's what we're going to do. So conveniently, I've because F7 just runs to the next return statement. All of these straightforward functions that only have one that are only one level deep. They don't. I can just hit F7 to essentially skip over the call, if you will. So here we're going to load up the address in RAM of our string buffer again. And then we're going to call getString. And if I tell it to just run to return, yeah, there we go. Ooh, oh, that's interesting. It's like very slowly single stepping for us. I don't know why it does this sometimes, but it should just continue running. But I guess because it's so slow, it's actually slowing each step. So now we're going to start putting in characters, see if we can't buffer overflow just for giggles. We're going to buffer overflow, and you see this is FFE0, and our string E0, yeah, is 32 bytes. So if we keep typing stuff into our input window here, let's just do a bunch of H's. Why not? We put it over here. Oh no, this is going to be a pain. It's sitting there flopping focus back and forth between the two windows. All right. So we're going to actually let it run to a stop. And actually to let it run to a stop, let's see. Now let's just let it run. Let's just first off fix up our source code, and then let's just let it. You bastard. Well, we're screwed now. I can't. It's not staying focused on the emulation long enough. There we go. To take a function key. So there we go. We managed to get into run mode, and that doesn't do all this single stepping for us. One day I'll figure that out, why that is. Again, not so stable. So now we're running along, if you will, sort of, kind of. And I think we can just start typing characters. Yep. So if we just start typing characters, you see we'll take up all of our 32 bytes. Just keep typing and typing. And there we go. So here's the very top of RAM. So in these kind of small systems, we have a single stack pointer. It's actually built into the processor itself. And it starts off at FF, and the stack grows downward. And the heap or compilation files would grow upwards, and hopefully they never cross, right? Because bad things happen when you overwrite your return address for your function. So this is actually the title of the next video I'm doing, or the subject of the next video I'm doing, which is the difference between jumps, which briefly, the jumps just overwrite the IP address or the instruction pointer address with a new one. Calls, which at a very minimum will put the return address, the next instruction, or rather the instruction upon which you said call. And you might say, well, I'm looking at this. What address? The address 0184D. What is that in my program, right? So that is the use of the map file. And if we go grab our map file, you'll see that, what is it? 014D, 014D is the instruction call get string. Now let's go ahead and put this into our YUP language. And yes, the files necessary to do this context sensitive coloring those files are in there as well. In the open source repo. Jesus. Some days. So now we say 014D is actually this call to get string, right? Now, if I keep overwriting stuff in my buffer, because my string function wasn't bothering to limit itself to a particular length of buffer, like a very bad standard C library function would like to do. So mem copy, string copy, any of the functions that only depend on looking for a null character, or in this case, looking for me to hit enter to just stop operating, they're pretty dangerous. That's where almost all of the headaches of security headaches of C come from. So as you can see, we're almost there. We're going to overwrite. Let's see now, to be all hacky about it. What address? Well, I can't even input these addresses because I can't input these bytes from the keyboard. I can't actually input 014D, but I could input, any other character. And in systems where, I'm not so low in memory, I could actually overwrite it to some other interesting address. In this case, we're just going to stomp on it with, I don't know. We'll just keep doing H's. Here we go. Now we've stomped on our return address, right? Now our return address from our function call is no longer this line that it was put at 014D. It's this line, 684D. Well, where in the world is that, right? It's not even in the memory map. It isn't programmed. So when I hit enter, it's then going to put a 0 here So we're actually going to say our return address is 6800. So if we, let's halt the system first, because otherwise it's all going to happen too fast. So if I put here carriage return into port 0, and I single step a little bit here, we're going to load into B that carriage return. We're going to then say, oh, that's not a 0. So we'll jump down here. Then we're going to acknowledge our character like we did before. Load 0A into A. Subtract A from A, which gives us a 0. We're going to jump if it's anything other than 0, but it is 0. So instead we fall through to store the contents of A over here. We do that. And now we're ready to return. But the return instruction is going to load 6800 into the instruction pointer. So let's see it do that. Well, I take it back. The reason it loaded 6803 was because normally a call instruction is 3 bytes, the instruction and the 2 bytes of the destination. So once you return, you actually have to skip over those 2 bytes that you were originally at. So now we're in location 6803, and one of the useful things of our assembler is it just simply installs everywhere in the ROM that isn't something that you're actually doing becomes a halt instruction. So this prevents it from going off into the weeds. You could also make that the reset instruction, and probably should, because what happens now is the system just halts, and that's essentially my my halt. I could tell it to run again. It's just going to run to the next halt instruction, right? So let's go ahead and reset. I forget what the reset is. Oh, F4 is reset. All right. Reset our guy. We reprint everything conveniently down lower than we were before because I didn't clear the screen properly. But there we are. We're now back to where we were, collecting characters. If we do that faster, and maybe not 6.8, what would be something within our memory map that would be some other instruction that we want to operate? So even though I have a separate ROM and only the instruction pointer can only be loaded from ROM, I say that now, but that's also, don't pay attention to these instructions here. Load into the instruction register, either the that's store, rather, these ones. Some days you're smarter than you think you are, huh? So this is the I and the P are the instruction pointer combined. And this is because you wouldn't normally copy from a register like the A register or the B register into the instruction pointer, because that can cause bad things to happen. Although some did, and that makes some nice convenient a convenient self-modifying code, if you will. So these rows are then used for the jump instructions instead. In fact, I had a concept at one point of a jump short based off of what's in the B register, which would be kind of like a self-modifying code, but I haven't actually implemented that instruction yet. So yeah, set everything else that you're not using to halt instructions. Actually, you should really set them to reset instructions, which is, what is that, AA, right? So that would be the other way. Or you could set them all to zeros, which would be no op. And it would just run until it finally got to the end of ROM and then start over at the beginning of ROM, which doesn't take too terribly long at 5 or 6 megahertz, but took forever in the Logicin simulation. So we actually managed to execute a buffer overflow attack while we were demonstrating this. But we want to be somewhere in our memory map. So let's see, our hello world map ends at 015A. If we look at the IO memory map, let's see, programs, IOlib, IO map. Yeah, that's all in the same similar. So what we want to do is, well, we can't leave it at, we can't make a 1 because we can't type in a 1 at the keyboard. But we could jump down into the 0 world, right? So we could effectively create a buffer overflow that causes it to reset, because we could cause it to go into just an odd location, right? Let's see if we can make that odd location happen. This time we're going to fill it all with G's. And then instead of, let's make sure I didn't overdo it. And then if we hit enter now, this will become 0, and we'll jump to location 0, 4D plus 3, DEF, or EF, so 50 in ROM. So what is that location 50 in ROM? Probably nothing. Probably more halt instructions. But you're beginning to get the idea of how you could use this to hack into something, right? Let's go ahead and halt for the moment and do our single steps. Oh, quit that. There we go. I got our carriage return in there. So now we're going to change this to 0. Write the 0, load A, subtract the 2, jump. If it's not 0, it is 0. So we're going to store 0. Then we're going to return. And now our IP address is 050, which is conveniently something. Oddly enough, it's, look at it, is for help on the emulation. So in our hello world map, here we go. Here we go. We're actually jumping into the string constant that we had in ROM. God knows what that's going to do, right? I mean, first off, the PDS instruction. Let's see. PDS, it's interpreting the, is it the space? 50, let's see. This would be 4A, B, C, D, E, F. G, it's actually the, which is PDS. So space character is 20 in hexadecimal, yay. And there it is. Sure enough, we're interpreting the space character, which is 20 hexadecimal, as the PDS instruction. I forget what the PDS instruction does, but it's probably not great. Oh, it does some pointer copies. Let's see, pointer copy. PSD and PDS copies the values of the data. You can't read that, can you? Uh-oh. Come on now. There we go. PSD and PS copies the value of the data register to the stack pointer. How convenient. That'll really mess us up. So now we're interpreting a space character as an instruction, and that instruction is to basically copy the current stack pointer value into the data register. So if we execute this instruction, the DR should become the SP. Let's see if it behaves like we think it does. Yep. Oh, no, not quite. Oh. Well, that confused things, didn't it? We loaded the stack pointer into the data register. Then we went to move to the next instruction. FFFF becomes 0, and then we end up back at main. So anyway, ways to screw up your code, all sorts of ways, huh? Jump around in code, execute strings. That's all kind of messy. All of these reasons are why you want to use bounded string functions in your C code. All of the ones that are string in copy or um, any input function that uses a string in C, you want to bound it to limit it so that it doesn't overdo or doesn't do a buffer overflow, because these kinds of buffer overflows is not just how you end up hacking it, it's how you end up totally confusing it. So I think we're probably safe if we tell it to run from here. There we go. We print out. Oh, confusing it. All right. Oh. Well, I think we killed it. All right. Obviously, the emulation is not really designed to handle that much screwing around. Well, it's been fun. If you guys don't have any other questions, we're going to go ahead and call it for today. Feel free to like and subscribe. And if you'd like to help me get through some of these bugs and dedicate a little more time to it, you can support me on Patreon. We keep it really simple. There's a $3 a month or $10 a month. Don't have a whole lot of complicated stuff. We do have some giveaways. Originally, all of this source code was part of the Patreon, but we've gone ahead and decided to put it up on open source under GitHub, just because it increases accessibility. And what I'd really like to see, just thrill me to no end, is if you're a instructor at college or high school level and you want to use these as part of your class to give people an insight into the complex instruction set architecture of micro-coded processors. That would just be great. I'd love to see that. Obviously, everything that you need to actually compile your own code. We actually have some other code, some games that we've been working on. But again, emulator is not completely stable. So forgive me if it goes sideways. But I think that's just about it, unless there's any other questions. Questions? Bueller. More 80 references. Huh? I'll ask in the chat, just so in case anyone's not listening. And then let's see. Do I want to save what I did to this file or not? I don't know. I might just not save what I did to this file. Yeah. Those things are okay. That's safe enough. And let's see if we go ahead and get Logisim going up here. If we go ahead and close that out, we should. No, don't want to do anything. That should save some processor cycles, and our emulation should be able to run a little better. I keep forgetting that I accidentally did that. So I think I have this set up where if I hit F7 inside Notepad, if I hit F7 inside Notepad, it actually precompiles the shell program. It's just hard-coded to always be the shell program. At one point, I had it would compile whatever file you had open. But in this case, it precompiles the shell program and then runs it. Oh, God, it is still running. Ooh, look at the slow. Oh, geez, it's slow. 5 megahertz. What else? I'm assuming this is this slow because we've got so much else going on. When I'm working and not streaming, this can get upwards of 35 megahertz in the emulation. But here was the basic shell of a shell program. There's our lovely mascot, Shelldon. He's named that because I misspelled his name, and it's going to stay that way because it's not worth changing. Let's see. Put in a question mark. Come back with a list of commands. Let's see. One of them, which is you can print the ASCII table. And that's convenient for figuring out all these box drawing characters. We clear the screen. and actually bring it back to here. Let's see what else we got. Oh yeah, a couple of useful things. Like if you wanted to show a set of hex values as characters. So I did this, but then I want to show, I can say D, where is it? Let's see. Let's say D, then DA, which is this character, and then C4, and then the other guy. Where's your other guy? Let's just do D9 because that'll be interesting. So then when we hit the enter, oh, needs a space. Sorry. DA, C4, D9. There we go. That was all just so I could figure out the box drawings and such. What's EUP Invaders? Well, it was a very small framework of a game. Let's see how well it behaves at this slow framework. It even has some sound. And let's see. Oh, yeah. ASDF for the motion. And let's see where. Woo, slow. Oh, that's a little too slow right now. And unfortunately, you're not able to hear it. But in any case, it's the basic framework for a Space Invaders type game. Hi there, Last Raz. How you doing? Yeah, and I'm still in the midst of producing or modifying this. One of the glitches I have is all of these character colors and special characters and being able to just draw the character screen over and over again. All of that is utilizing the ANSI escape codes. And the ANSI escape codes, unfortunately, or fortunately, are more straightforward, more readily understood in the display system than they are in my emulation. Long story short, I surround it with escape. So you do things like escape 16:22M or something like that, and that would say move the cursor to this position on screen, and then I print the dot. And then I say move the cursor up 1 and back 1 using a different command. Anyway, long story short, sometimes those commands get chopped up in the transfer from the emulation to the display, and that causes it to display the information instead of do the thing. So display the command instead of doing the command. Very annoying. So I do have a little clear function that'll clear the screen for you in case that happens. But anyway, we'll eventually get around to making it do things like when you fire the button, it actually hits the shield. And the goal was that the shield would, let's see if I, what is it? Quit. There it is. Yeah, there, quit and restart. You'll see that the shields kind of come into existence. That happens a lot faster when you're running a lot faster, obviously. But they come into existence using those different shaded characters. Using these different shaded characters, B0, B1, B2, and then DB. Well, I'm sorry. Yeah. We are basically running super low at the assembly level and doing things with an emulated processor. So to hopefully get you back a little bit back into speed, what we have here is an emulated 8-bit microprocessor or microcontroller. The difference being microcontrollers have more I/O, really. And then what we have here is the A, B, and T registers. If you ever do any assembly in x86, They're named differently, but they essentially do the same thing. Then we have a data pointer or a data register, a stack pointer, instruction pointer, what we're loading as the next instruction into the instruction register, and then what we have in our ports. Then all of this over here is the sequencer, which actually decrypts the instruction and executes all of the low-level commands and actual electronic signals to move data around in the processor. So if you're not at all familiar with assembly, it's a bit of a leap. Once you do a couple of things in assembly, either 6502 assembly, which there's a whole slew of videos on 6502 processor because it was used in the VIC-20 and the Apple II and just a whole slew of other game systems and early game systems. So the 6502 processor is also another approachable one. The downside is if you really wanted to do something, you'd have to run a 6502 emulation. And they do have those out there as well. So if you really want to get into it and not have I guess the headaches that I have here, where I'm not completely obvious, it's not all completely working yet, if you will. I would recommend going to find what is it called, 6502.org.
Yep.
Yeah, it can be like that. So yeah, it's oddly a lot of information, but it's broken down to a few very simple instructions. It's like all of the instructions in my assembler are fit on one page. In fact, they're all right here. Yeah, if my poor slow machine. So these are all the instructions for the assembler. You can have a command character, include a file, set the origin inside ROM, the next address inside ROM, create a constant, create literal constants of characters, create a constant name like a symbol, create a string of characters, write the contents of a constant to ROM, which is almost exclusively used for the reset vector, so that it knows where main is. Then define a constant, and this is primarily done so if you want to have a constant like, my headache equals 55 or something like that, age equals 55, something like that. That would be a constant. Then if there's a space character, and this is all about the first column of your instructions, so all of these guys over here. So the first column, and yes, it is space and column sensitive, like the old ones. So if there's a space, the next thing it expects is the 3-letter acronym for the instruction. And TLA, like I love to say, TLA is a TLA for a TLA. It is a 3-letter acronym for 3-letter acronym, but it is also the instructions for assembly. A lot of assembly languages will limit to 3, maybe 4 letters for the instruction. And then, that's it. You can create a variable, a name we replace an address in RAM with a variable name, or replace an address in ROM with a constant name. Or you could increase those addresses to create a buffer. So like in our Hello World program up here, where'd you go? Here we go. So in our Hello World program, we did what is the equivalent of one line in C of create a string named CA string with 32 bytes of space. We do that with 2 commands. Cut down the whole thing. Well, I do have a whole series of videos on this that start at different levels, especially when I didn't have the assembler yet or the emulator yet, and I was working just in the electrical assembly. So if you check out the playlist and just run down to the bottom one, that kind of starts at the beginning of all that. So I'm actually kind of looping around here. I very much welcome questions and any other things you might have. And who was it? I get the name right here. Is it Seven Etsu? If what's Tetsu? All right. Well, if you want to, feel free to to go into the repo and continue work on the EUP Invaders code or create your own game. I actually created a series of cards for card games, because when these kind of computers first came out, everybody assumed people were just going to write games with them, partly because they had such limited resources. So let's see if we open up in the programs, in the game libs, cards, we have a whole series of constants that define a card deck, and then do things like draw a card, shuffle the deck, this kind of thing. So this is all this is for figuring out what card is what, the mapping. So deck of cards, 7 of clubs, for example. Yes, we're doing with assembly language, and worse yet, I'm doing a custom assembly language that I created for a custom piece of hardware that exists only on only in virtual space. So it doesn't run quickly. But here you see the actual strings of bytes that actually define actually this first set of bytes is the row. This set of bytes here is those escape characters. So, bracket 5D escape, which is 27. Bracket 5D actually says go down, down 1 row. Actually, I take that back. It says go back 5 characters. So if I print these bytes, I then say go down, go back 5 characters, and go down 1 row and print the next set of bytes. So I'm actually embedding the escape sequence in the constant for the card, so that I only have to say where the top left character is of the card, say print this all as 1 long string, because here's the null character that ends this string of characters. So I can just say, here's your upper left-hand corner, print that card, and it'll actually print the card in that shape. It was sort of a trade-off, Obviously, I could have said print each row and then print the constant for move down and back. It was just easier to block and copy it in source. I have a lot of space in ROM relative to most real processors. So doing it that way means that, like I said, I can just say, here's my upper left corner, print it. And at one point I was working on a solitaire concept. This is, there's the whole screen, 80 characters by 25 lines. And so this was going to be my layout for a solitaire game. Oh, don't feel like that. There's lots of ways of coding, and this is fairly esoteric, if you will. Most developers nowadays are not going to get into assembly language unless they run into a problem of some sort of I/O. And even then, most of the assembly is obfuscated behind either behind a C compiler at least. But if not a C compiler, then also like Python script interpreter, which is also implemented in C. And so you don't really need to learn assembly. It's just the sort of the lowest building block of a processor. So, don't get discouraged if this seems really, really out there. I don't know. I probably should not say how many people I think actually do this for a living, because it's really hard to estimate. But I do a lot of embedded aerospace code. And because it's embedded, we're actually talking directly to hardware in a lot of cases. And in some cases, in order to do that communication quickly, it's easier to write it in assembly. So one of the things I encourage, if you code in C, there's an ASM keyword that's in the C language that allows you to open up a block and do specific assembly instructions just for that block within an otherwise C language function. And that's a good way to learn assembly for, in most people's cases, x86 assembly. So, it's, I guess if to help you out, I haven't a clue how to code anything in Rust, for example. It's a newer language. I haven't even really looked at it. So, I'm C++ for 30 odd years. Also done BASIC. I've done some Python and those kinds of things, but mostly I did Python to do things like repeat a bunch of functionality that is in a text file. So to modify text files, and then those text files are compiled using C. So that's why I would write a Python script. I wouldn't usually write a Python script to operate electronics directly. So anyway, again, don't get discouraged. It's all just a matter of what you concentrate on. So, any other questions out there? Let's see. Let's see what else we got. So you'll notice I did not get so verbose in the instructions when I'm not building a file for a demonstration where I put in 80% comments. I'm much less verbose in the comments, as most people are. So the reason you have these sort of lookup tables, everything's a lookup table. The processor itself is just a bunch of lookup tables. Take an instruction, use that as an address into one ROM. That gives you 16 bits of data. Use 8 of those 16 bits of data to look up an address in another ROM. That other ROM is 32 bits of data, and that tells all those bits actually become electrical signals to the different locations. So same kind of thing here. I have a lot of, let's see, when you go down here, these cards are very large, right? So I couldn't just start at the top of the deck and say card number 15 to look up this card in this big long table of strings. What is that then? Ah, all right. So, I don't have enough space. Is the long and the short of it is I've got 16 bits. If I started my address up there and I said multiply by 15, I'd be long way out of the way, right? I wouldn't be able to look it up. So instead of looking up the cards directly in this table of strings, I have a table of entry points. So this is the deck of cards index. So I can start a deck of cards index, and it only takes, what is this? So I can say load deck of card index, multiply 15 by, multiply card 15 by 3, the index size, and then I can keep my index size within 255 byte offset. So that looks up which address I'm actually going to look up. So I look up the address of the card in the card address lookup table. Then I have an entry level. Then I have an entry that I can find and load for the actual string that I want to print, which is all of this. So it's a lot of lookup table indirect over and over again, if you will. But it's because we have limited sizes. If I had a 32-bit machine, it'd be no problem to just start at the top of this deck of cards, know that every card is, what is it? I don't know what, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So 15 times 3 plus 45, 46, 47, 48, 49, 50, 51. So every card takes 51 bytes. And there's 52 cards. So if I multiplied or tried to find card 15 and multiplied by 51, I'd blow up my 255 byte value. If I were on a 32-bit machine, it'd be no problem, right? Which is why everybody moved to bigger and bigger address machines to avoid these kinds of headaches. I kind of enjoy these headaches because, I guess, mostly because it's unique to me. I'm not quite as far off in the weeds as Mr. Terry Davis was, but he created his own operating system and everything on the VIC-20 or the Commodore 64. So if you get a chance, do a search on YouTube for Terry Davis and Temple OS, and you will see a similar kind of madness, if you will, of doing it all from scratch for yourself, by yourself, if you will. But I don't want to do it all by myself, especially when it comes to the games and so forth. Alrighty. So we have all sorts of infrastructure in there that I've done, because of course, I got it to print cards. And so now let's move on to doing something else, right? There we are back at the Yup Invaders. Let's see. Eventually I'll add, the ability to run the other games. Let's see. The Yup Out game, which is actually more like Snake. And all it amounts to is, look, I can draw a line. Yeah, this is all of the emulation is done in C, and the assembler is done in C. When at one point I thought I was going to be able to make a useful game for Facebook, and while it is a game on Facebook, that's all done in HTML5 and JavaScript and so forth, and that's called Flingo, Fly and Go. It's a version of Bingo, a combination of Bingo and Kino, really. What now? Yeah, it's something of a slot machine, but the theme is Bingo and Kino sort of combined. It's still up, it's still running. I don't do much with it, but in any case, it's up there. Yeah. Yeah, the specs of this machine are CRAPY, double PY. That's the specs of this machine. It's a laptop. Actually, it's an Intel Core i3 laptop that is taking the place of my main machine because my main machine's hard drive went silly, and I just now got the replacement and haven't gotten it all set up again. So we'll get it set up, and next time we'll have a lot more interesting throughput. In fact, you guys can't hear the sound on here anyway. Yeah, well, you can't hear the sound of the game. Really, my voice sounds as bad too? Ugh. Don't try and stream from a crappy i3 machine, I guess. That's the lesson there. Either that or don't run a hardware emulation and a software emulation. And so, like I said, next stream, we'll put this new hard drive that I literally just got this afternoon. We'll put that new hard drive back in my tower machine, which is got a nice GPU and everything. And assuming that the old hard drive didn't die because of the power supply in my old machine, that hard drive will live, hopefully, for a while. But we're just going to go Linux on it. Oh, yeah. Yeah, especially in my usual setup. So right now I'm just using StreamYard, and it's just my camera overlaying the screen capture. But in what I normally do is I use OBS Studio to put together a scene, and then that becomes a virtual camera that is used on StreamYard, and then StreamYard just looks at my camera full screen, and then I do everything else through OBS Studio, which I don't even dare bring up on this machine for fear that it completely comes to a screeching halt. So let's see, what else did we got in here? Oh yeah, we can echo a string surrounding it with escape characters as a VT command. So this is the so let's see. Let's see here, because actually I have those as well. Got to make an include file, don't you know? So in the display libs folder, we have the VT100 commands that I can generally just call but like say, for example, if I want to send the cursor to the home, I can just load that up and print it. But to test different commands, I created a V interface here in the shell. So V is a substitute for escape, since otherwise I would exit the program. And if I want to go home, I say escape E 7:1 capital H and hit enter. Oh, and it did not understand it. Why did you not? Oh, I don't need the E. That's why. See, that's the kind of thing that would happen. Instead of actually executing the command, it would echo the command. And that happens a lot when I'm doing things quickly with the game. But here, if we do echo, there's V. I just need bracket 7:1 capital H. And then now my cursor's back up here. And then I printed out the S colon. So let's clear the screen. Let's try some other ones. Let's see. Most of these, a lot of these don't work because, ancient history. But here, if I wanted to do blue on black to change the colors, I can just print in code. I print. I do LDR for load the address of the VT red on black constant, and then I say print from ROM, and it prints out those characters. In here in the shell command, we'll just do bracket 31, 40M. Oh, I did red on black. Sorry. And so anyway, that's how you modify the colors and reverse character. Let's see if we do reverse character, that is bracket 7M. There we go. Clear screen. Print out the hex or the hex, the help. So let's see what else we did. Test runs the latest test code. There's a function called test function, and there it goes. Right now, it's conveniently doing an exercise. Oh, there, it screwed up. See, queue is full. So I've got a queue between the thread that is running the virtual processor and the thread that is drawing the screen. And as you can see, if you run it too quickly, the queue fills up and then goofiness happens. So I think at this point I can only exit out. But that was a test of me of the code for conversion of numbers to decimal. To what is it? I20A in the C language. Essentially an example of that, but it's just running constantly and clearly running too quickly for my display system. So, we hit the 2-hour mark. Well, again, I'd like to thank everybody for joining me I know I try and stop, but it's just so encouraging to have that many people, this many people watching for once. That I hope you all bookmark and follow and all those fun things, and join me next time. Hopefully we'll have a far less resource constrained machine, and it'll be a lot more straightforward. So thanks all, and we'll see you next time. And like I said, streaming all these times to 2 and 3 people has been somewhat frustrating. It's very encouraging to get this many. And well, like I said, we'll see you next time. Thanks. Let me find the button here. Bye. Oh, got to hit 2 buttons.